In this video, we're going to look a little further at the rigid body kinetics of a roller rolling down a ramp without slipping. In the previous video, we solved this problem by writing the equations of motion and calculating the acceleration, and from that calculating the time and it would take to get to the bottom of the ramp, as well as the velocity when we get to the bottom of the ramp. We check that by verifying the solution with the conservation of energy to find the velocity at the bottom, and we also ran a SolidWorks simulation and found that our time and velocity matched up well. But the problem statement again just said that the roller rolls without slipping. It doesn't give us a coefficient of friction. So when we ran the simulation, we just picked an arbitrary, relatively high value of 0.5 as coefficient of friction, and since the numbers matched up, we assumed that was good enough to prevent it from slipping. And what we want to do is look at that a little further and determine what coefficient of friction would be required to prevent the roller from slipping. And if we do have slipping, can we still determine the time to get to the bottom and the velocity? Well, here's the ramp geometry. It's a 30-degree angle. The roller will drop 3 meters as it goes down this 30-degree slope, which means it'll end up traveling a total of 6 meters from the top to the bottom. The roller details we looked at last time. We used SolidWorks to calculate both the mass and the mass moment of inertia, since we have a relatively complex shape. And we drew a free body diagram. So we took the sum of the force in the x, sum of the forces in the y, and it turned out that the only equation we really needed to use was the sum of the moments. And we had a choice of taking the sum of the moments about the center of mass, or taking the sum of the moments about an axis through point O, because of the fact that point O is an instant center, because again the problem statement says it rolls without slipping. Then we have the relatively simple equation that the sum of the moments about that point is equal to the mass moment of inertia about an axis through that point times the angular acceleration alpha. And of course we also have the equation that relates the acceleration of the center of mass to the angular acceleration. And so we went through this last time. We put in all of our known values. We started out by finding the moment of inertia about an axis through point O. We used the parallel axis theorem for that. And then we put in all our known values into the sum of the moment equation. So here we have the weight, which is the mass times g, times the sine of the 30-degree ramp angle, times the radius of 0.1 meter, and we set that equal to the moment of inertia. We just calculated times alpha and solved for alpha. It's about 30.7 radians per second squared. And to find the acceleration of the center of mass, then we simply multiply that by the radius and come up with a little over 3 meters per second squared. Okay, now we did that last time, and we were able then to just integrate that once for velocity, integrate with respect to time to get velocity, I should say, and integrated that again to get the position. And we were able to solve for the time that it would take to go 6 meters and the velocity that corresponds to that. Now, we can go back to our equations that we didn't use earlier, that is the sum of the forces in the x. Here we know everything except for the friction force. So we can put in our known values, again the weight, the mass times g, the sine of the 30-degree angle, and on the right side of the equation the mass times the acceleration we just calculated, and we come up with a friction force of 73.5 newtons. Looking at our equation for the sum of the forces in the y direction, of course there's no acceleration in the direction perpendicular to the ramp, so we're able to solve for the normal force, this being the weight times the cosine of the ramp angle 30 degrees, and that turns out to be about 340 newtons. So if we look at that and also look at the friction we just calculated, if we're on the verge of slipping, in other words, if to calculate the minimum coefficient of friction that's required, we set the friction force equal to the static coefficient of friction times the normal force. That's the maximum friction force we can have. And so it turns out that the coefficient of friction is 0.22. So if we're greater than that, which we were in our simulation with 0.5, then we are not going to slip. Let's go back and look at our SolidWorks simulation again. And so running this with that high value of friction that we guessed at, we assumed that there was no slipping here, and when we got to the looked at the the plot here of the velocity as a function of time, and we did see that it's slightly under 2 seconds. Let me change this for just a little bit. Yeah, just slightly less than 2 seconds, we achieve a velocity of about 6 meters per second, which matched up with the calculations. But we also said that if we plot the trace path, which is the path that's followed by one point on the perimeter of the roller, we can see from the shape of that that we are rolling without slipping, that that point becomes an instant center at each of these cusps right here. Now, as a comparison, we set an arbitrarily low value of friction, and in this case a kinetic coefficient of friction of 0.1 and a static coefficient of friction of 0.15. And based on the fact that the velocity is much higher at 7 meters per second, and also we do reach the bottom faster, then we can assume that there was some slipping going on, as well as about 1.7 seconds, by the way, some slipping as well going on, as well as rolling. And when we look at the trace path, that becomes pretty obvious as well, that we are sliding as we're rolling. Now, if we want to know how accurate our 0.22 is, we could try a value just slightly below that. So in this case, we've put in a value of 0.2 for both the kinetic and the static coefficient of friction. And it's kind of hard to tell by looking at it whether we're sliding or not. And in fact, even if I look at the trace path, it looks a little different, but it's not, we don't see the exaggerated curve that we see at the base of the very low friction values. But one thing we can do is look at and see that we've how many revolutions that we've made, because each one of these cycles is a revolution, and you can see that we've made a little over 8 revolutions here. Whereas if we go back to the case where we had a high coefficient of friction, a value that was above the 0.22 value, you can see that we actually make a little over 9, maybe 9.5, 9 3/4 revolutions. So even at a coefficient of friction of 0.2, we do see evidence that that we were slipping as well as rolling. Let's go back to this one, though, the case where we have a static coefficient of friction of 0.15 and a kinetic coefficient of friction of 0.1. And let's see if we can match up the values that we showed here of about kind of a bug in SolidWorks that it doesn't remember these axis properties. But you can see we're at about 1.7 seconds to get to the bottom and about 7 meters per second. Let's see if we can calculate those values. Okay, so there's our again our values that we're going to look at. We know that slipping will occur because of our static coefficient of friction being less than the critical value that we calculated. And so in that case, the friction force is going to be the kinetic coefficient of friction times the normal force. We calculated the normal force earlier, and so our friction force is going to be 33.97 newtons. And if we look at the sum of the forces in the x direction here, now the only thing that is an unknown here would be the acceleration of the center of mass, and that comes out to be 4.055 meters per second squared. And so we can integrate that twice with respect to time to get both the velocity and the position. And with the initial position and initial velocity both being equal to 0, we can solve for the time it takes to move 6 meters and find that that is 1.72 seconds, which matches up uh, with the graph we just showed. And the velocity then, we can simply take the acceleration, multiply that by the time, and again, right about 7 meters per second, so that looks okay as well. One thing we could ask, though, is that how many revolutions is the roller going to make as it moves down the ramp? Again, knowing that it's both sliding and rolling at this point. And so now it makes sense to take the sum of the moments about the center of mass, the axis that we got out of the value that we got out of SolidWorks, because it's easy to calculate the moment here because we know the friction force, and so we can solve that directly for alpha. Interesting to note, we cannot use that point of contact the same way we did before, because when we didn't have sliding, that was an instant center. Now it's just an arbitrary point, so the equation gets a little more complicated there. But again, we can always use the sum of the moments about the center of mass, or an axis through the center of mass. And so in this case, we know everything except alpha, and so we can solve alpha for as 14.17 radians per second squared. And so now all we have to do is integrate that twice with respect to time, and so we get the angular velocity and the angular displacement. And since we're, again, the angular velocity is, we're starting from rest, so that's equal to 0. The initial position, we can arbitrarily set that equal to 0. And so in the 1.72 seconds it takes to reach the bottom of the ramp, we could see that we'll have gone 20.96 radians. And converting that to revolutions, we simply divide by 2 pi. And so about 3 1/3 revolutions is our prediction. And if we go back and look at our trace path, you can see 1, 2, 3 full revolutions in about 1/3. So that looks matches up pretty well. Okay, one more video left here, and in the next part we're going to ask the question, we've looked at this and said, how does the mass come into play? We've used both the mass and the mass moment of inertia, so the question becomes, if we change both of those, what's going to be the effect? Do the heavier rollers get to the bottom first? How does the mass moment of inertia and the geometry affect that? 2 of these rollers are steel and 2 of them are plastic, so we can be thinking about which one do you think is going to get to the bottom faster, and we'll see you next time.